Assalamualaikum and good day. We are from EH2208I and we are going to present our design project 2 entitled Production of 130,000 metric tons of nitric acid per year.
Assalamualaikum, and my name is Fatih Nurul Akila binti Ishaq, and I will introduce you to our group design project on production of nitric acid. So nitric acid is used mainly in fertilizer industry. So our main goal is to produce nitric acid and produce 130,000 metric ton per year and to fulfill the gap of imported nitric acid in Malaysia. The process selection is through osmolar production to produce nitric acid. Our objective in production of nitric acid is to produce nitric acid that is suitable and high qualified for commercialized to the production market. The site location that have been chosen for the production of nitric acid is in Kerteh due to their advantages in land price, environmental, utility price, and accessibility. In the mass balance, the purity that we aim for our production is 68% and catalyst platinum rhodium will be incorporated into the production. Our target production will be 130,000 tonnes per year. The energy balance for this production, we assume it to be in steady state. Kinetic and potential energy, heat of mixing, and effect of pressure drop are neglected. The reference state is at 25 degrees and 1 bar pressure in liquid and vapor state. From the figure shows the overall mass balance is balanced, which is 29,517 kg per hour. So overall mass balance and energy balance then compared to hypothesis with the manual calculation.
First thing first, the figure shows the process flow diagram before integration. Next, we go to process flow diagram after integration. As we can see, hot and cold utilities being added to the coolers and heaters. The table shows the stream data for the process after being shifted. In this production plant, the minimum approach temperature is selected based on the industrial application, which is 10 degrees Celsius. The stream is selected around the heat exchanger streamline, which consists of 5 cold streams and 5 hot streams. Next, we go to cascade diagram. Cascade diagram shows the net amount of energy in each temperature interval. From this diagram, we can obtain the value of pinch temperature and minimum requirement for hot and cold utilities. For pinch temperature, the value is 539 degrees Celsius, which we can see the value that is aligned with the zero cumulative value of enthalpy. The value for the minimum cooling and heating cooling are 12,304.54 kW and 680.68 kW respectively.
Assalamualaikum, my name is Nurul Afifah Zulkifli and I will proceed with heat exchanger network. The aim of heat exchanger network design is to recover as much energy as possible, whereas it consists of two components, which is heater and cooler. Based on figure 6, as heat is transferred from cold to hot streams, 5 heat exchangers are located. All cold stream heat loads have been shifted to hot streams, with the remaining loads became cold utilities. Figure 7 and Figure 8 show the heat exchanger network on above and below pinch. It can be concluded that only one hot utility involved for the above pinch, as it consists of 2 streams, and 5 cold utilities for the below pinch. The feasibility study is conducted by plotting the graph between the temperature and heat load. By referring to the above and below pinch TH diagram, all heat exchangers are feasible and show that value of delta T is equal or greater than delta T min. The diagram also shows that there is no streamline that cross between each other. The generated graph for grand composite curve can be observed from figure 10. For the above pinch region, the preferable utility is hot oil as the temperature is above 500 degrees Celsius. Hot oil was selected for the above pinch utilities as other types of utilities could not support a very high temperature. As for the below pinch area, utility selected is cooling water as the temperature is between 15 to 35 degrees Celsius.
Now, I will be presenting the catalytic reactor where the ammonia and oxygen will enter this reactor and produce nitrogen oxide and water. by using the catalyst of platinum rhodium. The objective of this reactor is to increase the process oxidation of ammonia, where about 93% of the ammonia will be converted into nitrogen oxide gas. The reactor will be operated at temperature of 900 degrees Celsius and operate at pressure of 7.2 bar. This is the chemical design for the catalytic reactor design. The chemical of the reactor is a plug flow reactor, and the orientation of this reactor is in vertical. The reactor has volume of 13.5 meter cube with a height of 6 meter and diameter of 2 meter. The material construction that shows for this reactor is stainless steel and it has an ellipsoidal head closure. The minimum of thickness of this reactor is 4.27 mm. This reactor also has installed a mineral wool used as insulator. This reactor has a skirt support, which is a straight cylinder skirt with a height of 2 meter. The catalyst in this reactor weighs about 33.12 kg. This reactor also has installed tube, which has 460 tubes. Next is the process control for the catalytic reactor. This reactor has been installed a temperature control, flow control, and pressure control. The temperature controller will be installed to the cooling medium to control the temperature of the reactor to prevent the reactor from overheat and to prevent the temperature drop from below set point, which can affect the quality of the desired product. The flow control is to control the inlet flow of ammonia and oxygen into the reactor at a desired set point to ensure to achieve desired production rate and prevent from flooding occur inside the reactor. The pressure controller is functioned to ensure there will be no backflow of the product into the reactor and also to prevent it from increasing above set point, which can cause damage to the reactor. It is also control the increasing and decreasing of the temperature inside the reactor. That's all from me. Thank you.
Assalamualaikum. I am Amina and I will be presenting on the equipment R101, an oxidation vessel column. The reaction that takes place in the equipment is oxidation of nitrogen monoxide, which is an exothermic reaction. The inlet stream temperature is 50 degrees C and the outlet stream temperature is 56 degrees C. The reactor chosen is tubular reactor as the reaction occurs is homogeneous gas phase reaction with no catalyst involved. Based on the chemical design calculation, the total volume of the R101 is 0.44 meter cube with 1.343 meter length and 0.65 meter diameter. The reactor consists of 139 tubes to increase the surface area for the reaction. Half cooling jacket is installed to maintain the operating condition of the reactor. A rock wool insulator is used. As the reaction does not involve any highly corrosive chemical and extreme operating condition, the material of construction used is carbon steel with an ellipsoidal head closure. The first process control used is feed-forward controller. A level transmitter will monitor the level of liquid inside the reactor and connect it to a feed-forward controller. If the liquid level increases above the appropriate level, a signal will be sent to stop the flow rate inlet from the stream 14. Second, a cascade controller to maintain the temperature of the vessel. The manipulated variable is the flow of the cooling water inside the cooling jacket. It is controlled based on the temperature data transmitted. Last but not least is the feedback controller. The pressure transmitter installed to monitor the pressure inside the vessel. In case of pressure buildup inside the reactor, a high alarm pressure will ring and the flow rate at the top outlet stream will be increased. Next is the safety measure of R101. If no reaction occurs, no product will produce, causing the buildup of reactant inside the reactor. An irregular flow of reactant may produce an off-spec product, while high flow inlet can cause a runaway reaction. Too high or too low temperature can cause the reaction to produce an off-spec product because of the unsuitable process condition. A very high temperature can also cause fire to the vessel. Over high pressure can cause burst of piping or tube. Worse, it can cause fire and explosion to the vessel.
Conversion reactor, also known as continuous stir tank reactor (CSTR V100), implemented in this process to achieve a reaction between NO2 (nitrogen dioxide) plus with water to produce nitric acid with NO gas at 7 bar and 82 degrees Celsius. This is an AutoCAD drawing of CSTR V100. Its height is 7.512 meter and its diameter is 2.503 meter. This reactor requires jacket because the process inside of the reactor and exothermic reaction. Material of construction for this reactor is using stainless steel SS316 and its minimum wall thickness is 9.0 mm. The type of head we use on this reactor is ellipsoidal due to its measurement were compatible with the size of reactor. So we move to the process control of V100. The process control will install in this equipment, ensure its safety and the efficiencies of the process. The first one is the temperature controller. The temperature controller will install to prevent from the temperature inside the reactor going over spike from the desired temperature. Next, the flow controller. The flow controller will install in order to maintain the flow rate of the feed into the reactor. Next, the pressure controller will use to prevent the pressure inside the reactor overpressure from its desired pressure. For the safety measure of CSTR V100, if the pressure is too low or too high, it will lead to the lower purity of product and the vessel will rupture. Thus, a spare valve or pipeline should be installed. The pressure alarm and indicator should be installed too. Next, if the flow is too low or too high, it will lead to the lower purity of product and also flooding to the reactor. Thus, the indicator and alarm should be installed. Lastly, the temperature. If it's too low or high, the desired temperature is not achieved. That will lead to the bad quality of product produced and it will create more waste state of product. The addition of cooling jacket is the solution to this issue, and also the installation of temperature alarm and indicator should be proposed as well.
Assalamualaikum, my name is Nurul Afifazul Kepli and I will present the design of heat exchanger E101. This heat exchanger is designed mainly to increase the inlet oxygen temperature to obtain the desired outlet temperature from 25 degrees Celsius to 300 degrees Celsius by using high pressure steam. The type of heat exchanger used is shell and tube heat exchanger with one shell and two tube passes through horizontal rotation and continuous operation. Due to the factor of fluid temperature and operating pressure, oxygen is allocated at the shell side as the cold fluid and high pressure steam is allocated at the tube side as the hot fluid. In accordance of designing a heater in this production, low carbon steel up to 0.3% of carbon has been chosen as the material of construction. Carbon steel is chosen as it has excellent corrosion resistance and can be used at both low and high temperature up to 800 degrees Celsius. The corrosion allowance is chosen at 4 mm where the expected corrosion might occur. For the type of heat exchanger head, ellipsoidal head is chosen with the value of thickness of 4.38 mm. Welding neck flange are used for the E101 and mineral wool is chosen as the type of heat insulator with the thickness of 75 mm. For this heat exchanger, cascade control is chosen as the control system due to the presence of two measurements to control the temperature. The output temperature of product stream is set as a control variable in the system. Meanwhile, the flow of steam entering the heat exchanger is set as the manipulated variable. Next, the flow and temperature parameter indicate the disturbance. In this regard, temperature transmitter is set up at the output stream of the heat exchanger. The temperature transmitter will determine the temperature and generate signal proportional to it. Control valve is located at the steam inlet stream to control the amount of steam required to be fed into the heat exchanger as the heating medium. Next, I will explain on the hazard study for heat exchanger E101. First, if there is high steam inlet flow, it will lead to sudden increase in temperature and explosion. This can be overcome by installing automatic valve. Second, in a situation where low steam temperature is applied, the possible consequences would be desired temperature deviates. Hence, automated temperature indicator should be installed. Lastly, high pressure steam will lead to bursting of tube due to the failure of steam inlet valve. This can be overcome through installing high temperature alarm.
My name is Nur Lukman Hakim bin Salih Rashid, and now I will continue the presentation of Chapter 9, Heat Exchanger E106. The objective of this heat exchanger is to cool down the nitrogen dioxide at a temperature of 241.8 degrees C to 50 degrees C. As shown in the table, it shows the component fractions at stream 17 and stream 18, which is consist of ammonia, oxygens, nitrogen dioxide, nitrogen oxide, and also water. At stream 17, the temperature is 241.8 degrees C with a pressure of 7.08 bar. Meanwhile, at stream 18, the temperature is 56 degrees C and the pressure is 7 bar. The medium coolant that will be used in this heat exchanger is cooling water at 30 degrees C. Let's proceed with the drawing of the heat exchanger E106. The type of heat exchanger is the shell and tube heat exchanger. The number of shell passes is 2. The number of tube passes is 2. The shell diameter is 274 mm. The tube inside diameter is 20 mm. The tube outside diameter is 25 mm. The tube length is 4880 mm. The type of head is ellipsoidal, and the corrosion allowance is 4 mm. And as for the material of construction, both shell and tube are using the carbon steel, and the insulator is mineral wool. Now proceed with the process control. The transmitter will be set up at the outlet stream of the heat exchanger, and it will measure the temperature at stream 18. The transmitter will create a signal and send a signal to the temperature controller, and the temperature controller will compare it with the set point. Other than that, the signal also will be sent to the flow controller if there is any deviations of the value of the temperature at the stream 18, and the control valve will control the inlet feed of the cooling water so that finally the target temperature at this outlet stream can be achieved. Now I'll continue with the safety of the heat exchanger E106. First, if the temperature of the cooling water is higher, the target temperature of the heat exchanger could not be achieved. Other than that, the explosion also might be happen, and there will be a production losses of the nitric acids. Second, if the flow rate of the cooling water is higher, the piping system of the heat exchanger could be ruptured, and there will be an increasing value of the temperature inside the heat exchanger, and hence the objective of the E106 was not successfully achieved.
Hi, my name is Nur Izwa binti Rahman, and I'm going to explain more on heat exchanger E108. Heat exchanger is a system to transfer heat between two or more fluids, and for heat exchanger E108, the objective is to increase the temperature of water from 30.05 degrees Celsius to 50 degrees Celsius. And as you can see here, the stream number 24 contains only water with temperature 30.05 degrees Celsius and the pressure is 6.1 bar, and it will be heated to 50 degrees Celsius. The medium used to heat the influent is hot water, which enter the heat exchanger at 82 degrees Celsius. The type of heat exchanger that has been chosen is shell and tube with BEU type, and the number of tube is 76 with 4 tube passes. Shell passes is 2, and the shell diameter is 296.38 mm. For tube inside diameter is 16 mm, and the outside diameter is 20 mm. The tube length is 5000 mm. Type of head is ellipsoidal, and the corrosion allowance is 4 mm. For material construction, both shell and tube is low carbon steel, and the insulator is mineral wool. This system will measure the outlet temperature and generate signal proportional to it. After that, the signal is sent to the controller where it is compared to the set point. If there is some temperature deviation at the outlet stream, the temperature controller's output signal will be sent to the flow controller. Next, the volume of water that must be fed into the heat exchanger is then controlled by a control valve located at the feed water stream. And finally, the temperature that is required can be reached. Okay, now I'll present the heat exchanger safety. First, no hot water flow. This can happen if there is a failure of the inlet valve. As a result, the mixture is not achieve the desired temperature. So in order to overcome this, flow sensor need to be installed. Second is less flow at tube side, caused by failure of inlet valve to fully open. As a result, there will be a production loss and the desired temperature is not successfully achieved. This situation can be avoided by provide regular inspection and install flow meter. However, if there is more flow at the tube side, instead of install flow meter and provide regular inspection, we can also take an action by install high temperature alarm. This can be happen when the control valve is malfunction, which later can cause too high temperature of the mixture. Next is temperature high, happen when the control valve is failed to close. This can lead to fire and explosion and also production loss. In order to overcome this, we can install control valve and high temperature alarm. Sometimes, production loss also can occur when the temperature is low. This caused by valve malfunction. Control valve and low temperature alarm can be installed in order to handle this issue.
Hello, I'm Amina. I will be explaining on the total equipment bare module cost. Bare module cost is one of the costing techniques used to ascertain the cost of plant build-up, to control the budget and help the decision-making process. The capture value used to calculate the bare module cost of the equipment is 607.5. This nitric acid plant consists of 3 reactors, an absorber, 5 compressors, 5 heaters, 5 coolers, 2 pumps, and 2 mixers. After totaling up all bare module costs of the equipment, the total bare module cost equipment equals to $5,933,705 or 24,446,863 Malaysian ringgit.
For non-discounted cumulative cash flow, our nitric acid production is estimated to have a project life of 10 years. Thus, this project is variable as its revenue is RM234 million ringgit. They will make a profit after 3 years of investment. Also, the rate of return of investment, which resulted in 16.60% per annum, will lead to a stable financial status. On discounted cumulative cash flow, there are significant effects of discounting the cash flows to the account for time value of money based on our calculation. First, the discounted rate increase as the payback period also increase in terms of time basis. As calculated, the value increased from 3 years to 4.5 years. So, we choose 0.1 as our discounted rate, which shows that our DCFROR value is higher than the initial discount rate. Thus, our production shows to be profitable.
Now I continue the presentation with Chapter 11, Plant Safety and Layout. There are a lot of types of emergency that could happen inside the nitric acid plant, such as natural disaster, fire, explosion, equipment failure, failure of facility, failure of utility, and also contaminations of the products. Therefore, the emergency response plan is needed for each type of emergency so that all the workers will be already prepared. Other than that, the emergency device also will be set up around the plant of nitric acid, such as fire alarm, fire water sprinkler, emergency lightning or exit wound with twin lights, fire extinguisher, fire escape ladder, safety sign and symbol, hose reel, and also closed circuit camera CCTV. The site location of our nitric acid plant is at Kerti Industrial Area Terengganu with a size of 871,199.69 feet square, which is equivalent to 20 acres. The figure shows the plant layout 3D dimension drawing of our nitric acid plant, which is it will consist of the chemical production area, control room, wastewater treatment plant, R&D laboratory, scheduled and non-scheduled waste storage, utility plant, administration building, cafe, guardhouse, parking lot, and 3 assembly point. Now let's proceed to the planning zoning area. So in our productions of nitric acids, there will be 3 zoning area, which is Zone 0, Zone 1, and Zone 2. For Zone 0, the area was indicated in the red color. In this area, this is the most high risk area that to be exposed to the explosive gas, and the accident situations is very easy to be happen in this area. Second zone is zone 1. This area was indicated in the yellow color. This area is slightly safer to be compared to the red zone, but the existence of the explosive gas can still be detected in this area, and the probability of the accident situation to be happen in this area is still could be happen. And the last one is the zone 2. So zone 2 was indicated in the green color, and this is the most safer area to be compared to the zone red and zone yellow, which is it's the most least area that been exposed to the explosive gas. Figure 35 show the exit or entrance and evacuation route of the plant layout, and also the nearest assembly point accordingly to the location plan of the fabrication facilities inside the plant.